This section is all about magnitudes. So a little bit of historical context. In about 129 BC, the Greek astronomer Hipparchus made a catalog. And at the time, to him it made sense to say, oh, well, the brightest ones are first magnitude, and the faintest ones that I can see are sixth magnitude. A little bit later, 140 AD, Ptolemy found this book and copied the system. And then Ptolemy formed the base of the astronomy texts for the next 1400 years. So we are stuck with this weird system where big numbers mean fainter. So a magnitude, it turns out, when you define it mathematically, is really a flux ratio. It's logarithmic because our eyes respond logarithmically, and Ptolemy defined this system based on what he could see with his eyes. So a magnitude is really a flux ratio. So you have this definition, a magnitude of one source minus the magnitude of another source is 2.5 times the log of the ratio of the fluxes. So look, M2 is the second one here, but F2 is in the numerator here. That's where you get that inversion where you end up with brighter sources having smaller numbers. So the magnitude system in the optical is defined entirely as reference to Vega. So Vega is defined to be zero magnitude. So if you put Vega in for source 2 here, you have M1 minus M2, but M2 is Vega, so it's defined to be 0, is 2.5 times the log of the ratio of the Vega flux to the source flux. So you get this. When they looked at Vega with IRAS, which was the first all-sky infrared survey in the 80s, they discovered that it in fact did not look at all like what they expected. And in fact, Vega has a large infrared excess. So in the infrared, it's even more complicated because the infrared magnitudes are defined with respect to what Vega would be if it didn't have an excess. So complicated, but still coming back to observations of Vega. So reminder that stars, of course, are going to get fainter when they're further away. So apparent magnitude, which is usually little m, is the brightness an object appears to us to have from when we're here and it's at whatever its true distance is. Absolute magnitude, in contrast, is the brightness an object would have if you moved it to a standard distance of 10 parsecs. And a parsec is 3.26 light years. So you end up, if you plug that math into the definition of magnitudes, you end up with m minus m. So apparent magnitude minus absolute magnitude is 5 log d, where the distance is given in parsecs, minus 5. So that's another good definition to remember. So what that means is further away is fainter, which means larger numbers. So one slide on units. So flux densities, which colloquially often get referred to as just fluxes, although technically fluxes are different than flux densities. Flux densities are energy per unit area, per unit time, per photon. So the amount of energy you're measuring, say, per square centimeter, per second, per photon. That's what is a flux density definition. So brighter sources have bigger numbers for flux densities. And flux densities are linear. In other words, something that has a flux density twice as much as something else is twice as bright. SEDs, when we plot them, are energy densities. So it's energy per photon. So you need to convert flux densities from energy per unit area per unit time per photon into energy density, energy per photon, before you plot in an SED. When you make an SED plot, it should be log-log. So energy density should be in the log and wavelength should be in the log. Magnitudes, remember, are flux ratios, and they are backwards in that brighter sources have smaller numbers. They are also logarithmic. So something at 5th magnitude is not twice as bright as something at 10th magnitude, is in fact 100 times brighter than something at 10th magnitude. So technically, I needed 2 slides for a digression on units. Making things even more confusing, Pan-STARRS and Sloan have a slightly different scheme. A lot of the people that worked on Sloan, which came first, and then Pan-STARRS, they study galaxies. So they have different definitions of magnitudes. They decided that it made sense not to calculate magnitudes with respect to vega, but instead with respect to a flat spectrum. So these are called AB magnitudes rather than vega magnitudes. So for that definition, instead of the vega flux in the definition of magnitude, you use 3631 Janskis for every band. So if you're measuring with respect to vega is going to have a different brightness at each band. If you're measuring with respect to a flat spectrum, the calibration, the comparison value is always 3631 Janskis for AB magnitudes. This makes a big difference in terms of what colors you'd expect to see for a star. That's because the people that you do a lot of the pan-stars in Sloan science are worrying about galaxies, not stars. So on behalf of stellar astronomers everywhere, I'm sorry for these different units, and I hate AB magnitudes too. If it makes you feel any better, the first time I encountered Sloan data, they were in units of nanomaggies, which is even worse. So it's a pain. If you don't have any other indication, you should assume it's vega-based magnitudes, but it is something we're going to have to worry about specifically in the context of pan-stars and Sloan data. So magnitudes. Remember that if you measure the magnitude of star or galaxy or the moon or the sun in one band, intrinsic to the calibration, you are implicitly comparing to vega because vega is defined to be zero magnitude. But what that means is if you measure the magnitude of a star or anything else in two different bands and compare them, the vega flux cancels out. Go and do it. You'll do the math. You can see that it works. So color, meaning the difference of two magnitudes, conventionally the shorter wavelength band minus the longer wavelength band, is actually a ratio of the fluxes. So when you say I have B minus V color, intrinsic to that, implicit in that, is I'm asking what is the ratio of that object in B compared to V. So it's often very useful to do this because you can take the same object and compare its brightness. It's easiest to think of it as a ratio of flux densities, in other words, a difference of magnitudes, and it is in fact always the bluer minus the redder, so B minus V or J minus K. And if you stick to that convention, that means that larger numbers are redder and smaller numbers are bluer. So if you have a red star, which I mean a star that has an R magnitude, a brighter R magnitude, smaller number, brighter measurement in red than in, say, the blue band, then that star is going to be red whether it is close or far away. Just like with stoplight. A stoplight is going to be red whether you're close to it or far away from it. And something that's blue or green is going to be blue or green whether I'm close or far away from it. That's not going to change with distance. The brightness is going to change with distance, but not the color. So if the star is farther away, it's fainter in both blue and red, but the ratio of intensities doesn't change with distance. What does change is if you change the object. If the object is hotter, they're going to get bluer. If the objects are redder, they're generally cooler. So the main takeaway points from this are the definition of magnitudes and the fact that there's an implicit comparison to vega. So magnitudes are flux ratios. Magnitudes are backwards in that brighter sources have smaller numbers, and they are logarithmic in that something at fifth magnitude is 100 times brighter than something at 10th magnitude. AB magnitudes are fundamentally different than vega magnitudes. Colors are differences of magnitudes and therefore are also flux ratios. Magnitudes depend on distance, but colors do not. Colors are independent of distance. And colors are always bluer band minus the redder band.